Hello, everybody. I'm Stephen Foskett. I'm the organizer of Tech Field Day. The video you're about to watch is a recorded presentation of Intel's storage group presenting at Storage Field Day 11. The table is filled with invited delegates from around the world who focus on storage and storage-related technologies. They are bloggers and podcasters, and we've invited them here to participate in the discussion, to ask the questions that you would ask while you're watching. If you'd like to learn more about Storage Field Day or Tech Field Day generally, just go to techfieldday.com. If you enjoy this video, go to our YouTube channel, youtube.com/techfieldday, and you can subscribe and see literally thousands of other videos just like this one with all sorts of companies in storage, networking, wireless, and data center.
Thanks a lot for having me here. My name's Chris Silva. I'm a director of marketing in our channel group and our SSD division here at Intel. And what I wanted to talk about today is about give you a deep dive on our 3D NAND technology. We've been working for greater than 5 years on developing 3D NAND. It's an absolutely necessary transition in the market, moving from the planar NAND that we have today. We're running out of room, and so we needed to go to 3D in order to provide the types of benefits that we want to bring to the market. And I'll talk about that in a little more detail after we give you some of the technical details. But really, we believe that this transition to 3D NAND is going to transform storage economics. So we're all looking for that holy grail of when a particular solid-state device has the same cost per gigabyte as Rust, but we're not quite there yet. But through the innovations that a lot of our partners are driving, we're starting to see solutions that are actually less expensive in an all-flash type implementation versus a spinning disk type implementation. So when you start looking at total cost of ownership and the types of benefits that you can get from the speed of the storage, you're starting to see lower cost benefits, even without the bit level per gigabyte being at the same exact number. But we're driving there, and we're doing that through this 3D NAND transition. And as I mentioned, it's a technology we've been working on for over 5 years. We have one of our chief architects of this technology with us today. I'm proud to introduce Pranav, who's going to be talking to you here. He joins us from, he was telling me that he came to Intel straight from Stanford, where he was working on 3D transistors as part of your PhD. So this is what helps Intel to become this proven and trusted supplier we're talking about here. So with that, I'll let Pranav start walking you through some of the details of our 3D NAND.
Talk about a dream job.
Pretty close, actually. Pretty close. So before I delve into what 3D NAND is, which is the graphic I have on the very right-hand side for which is 2016 thing, just wanted to set the stage. So we've been talking about the software. We've been talking about how to communicate to the NAND. This is a very different deep dive into what the real silicon technology is that builds all of that. So dramatic change in the level of operation that we are trying to do. And this is talking about how we are building silicon and trying to set the stage for that. So Intel has been doing flash for a very long time. So we've been doing flash for almost more than 30 years, 3 decades. And on the left-hand side, it starts at 85. I was in elementary school at that time, so I won't take credit for building any of this. But this is where we started NOR. We were the technology leaders for a very long time, going all the way to 90 nanometer NOR. That was when I joined Intel and said, hey, let's start doing that. So we worked on NOR for a while, saw the whole transition coming from NOR to NAND. So was one of the first people who actually started working on NAND, and I've been working on NAND ever since. So we have a lot of technology nodes, 50 nanometer, 34, 25. And in every node, we don't have as much volume in our memory business. But where we make up for it is with our technology. So every technology, we have been effectively pioneers. So take an example, the 34 nanometer, we were the first in the entire industry to introduce pitch doubling in manufacturing. So what that does is it circumvents all kinds of lithographic limits, and we are able to print as fine structures as anybody else could without any advanced lithography, keeping the cost in check. So that was our innovation there. In 25 nanometers, we introduced a lot of things like air gaps all over. What they did was, to the end user, was performance. It just reduces the power needed for all the high-speed I/O that we want to do. And as a result, the whole 25 nanometer was that kind of a leadership. Again, the first of its kind in the industry. Then we jumped to 20 nanometer, and again, it was a different first. 2D was running out of steam. You can see that the storage nodes, that is the floating gate nodes, are pretty big. We went into a planar cell. We were the first and probably the only company who's done that. And we effectively introduced high-K, metal gate, all of those innovations in our 20 nanometer node, and kept Moore's law scaling for memory. That was then taken into a 16 nanometer, and then finally we realized, hey, we can't keep doing the 2D thing anymore. We can't just doing the expansion. We have to go vertical, and so we've started building the skyscrapers. So that's what we've been doing for these 30 years. To put things in perspective, we have, I think, qualified 17 generations of NAND flash, 17 generation of flash, NOR as well as NAND together. 12 of them have been MLC, so multi-level bit, and that builds a foundation towards going to TLC, so even more bits per cell. And we have improved the density by about 50,000 bits per millimeter squared. So a long journey, a long set of improvements, and that's where we are in terms of our 3D technology for Intel. So our technology is different than the rest of the technology that the industry has been going with. We are using a floating gate technology. So the entire 30 years of experience that I touted, we are effectively using that. So we have a 3D technology based on floating gate. Nobody else in the industry has that. And that offers us what we believe is the most important attribute, the highest areal density that we can offer in terms of memory or millimeters, gigabyte per millimeter squared. On the left-hand side is our showcase cross-section. Many attributes to that. So let me start with the left-hand top, which is showing just a series of dots as you look at it from the top. And that's our various pillars that we are going to form for our 3D NAND memory. It's a hexagonal closed stack structure, the classic things that you see in textbooks. And that's how we have actually built our top view. Looking at it from a cross-section point of view, you can see that, hey, on top we have the metal. We need metal for interconnections. And in the middle, we have these skyscrapers. Currently, we have 32 effective layers of memory. And another unique feature of our technology is that the entire CMOS, which controls all of these memories, sits below the array. So we call it the CMOS under the array. And what that does is, from a customer point of view, it effectively, think of it like it's a parking garage built under the skyscraper, so you're not really wasting parking lot space outside. And from a silicon wafer point of view, hey, you're getting pretty much active memory cells on every millimeter squared of the wafer that you're building. Anything that you need from a parking lot is all tucked into the under the array. So that's a very unique feature, again, one of its kind in the entire industry. So all of this together yields very good areal efficiency in our first technology itself, first generation. The competition does different kinds of things where they're trying to do some replacements gates, and they need all these kinds of vertical elevator shafts to make things. So that's just one of the examples that I've put here. But short takeaway here is in our very first technology node, which was our 32 nanometer node, our areal density is world class. We are the leaders in areal density. We have about a 10+% advantage in that. And again, for the end user or for the storage market, what that results in is, hey, we can, on a particular wafer, what we can do is we can make more gigabytes per wafer. You can think of number of wafers in the whole production fab being kind of constant. And the more gigabits you produce on a particular wafer, hey, the more SSDs we can actually build. So floating gate NAND, vertical 3D with CMOS under the array is our unique innovation in this particular area. What does this really mean? The name of the game in semiconductor industries is making things at a very high volume. And you want to be yielding at a very high mature level, have very few defects, and be able to make things in a large scale. We know the technology, floating gate flash. We have experience in high volume manufacturing, and so as a result, I think we are probably the only company who's saying that, hey, our 3D costs are unequivocally double digits lower than our 2D costs. There was no doubt in our mind that, hey, 3D is the future, and so we've gone there, and we are able to actually make 3D bits which are better than 2D bits from our very first technology. That is not necessarily true for the rest of the world. They're having a lot of replacement gate challenges in terms of yield and all that stuff. So just a few tidbits from other companies, Western Digital as well as Samsung, which are saying that, hey, it takes a while, 2017, 2018, to actually have a full bit crossover. We are already there in terms of being able to make
crossover to 3D.
So 2D to 3D, you have to invest a lot to make 3D things.
This refers to the crossover.
From 2D to 3D, exactly. All right, so taking a step back into what our structure really looks like. This is more trying to show what our storage nodes are and then compare and contrast with other technologies. But what it is really is you're building massive number of cells on the side wall of a particular pillar, the cross section that we saw earlier on, and that's how you get your efficiency. If you build 32 tiers, you can actually, in the same millimeter square of silicon, you are actually getting 32 memory cells in the particular silicon. So that's how 3D actually is winning in terms of cost. The unique structures that we have here is our floating gate structures are discretized. So we're making floating gates which are in the pockets, so to speak. And this is our claim to fame that, hey, we have excellent storage protection from any kind of charge loss. The 2 bits are physically isolated. And as a result, the non-volatile nature of the entire memory cell is unique and is exemplary in terms of what the technology choices can be. So the non-volatile memory really is non-volatile, so to speak, and as a result, we can actually go for reliability at a very, very compressed density. From there, so we have operated things at a technology level. You can take it up into the product level, unless there are any questions.
Any technical questions about how we've implemented 3D transistors and 3D NAND?
Have you guys built any 3D transistors or NAND like at home?
Not recently.
Yeah.
I'd be afraid of what's in Pranav's basement. So
It's only 2 layers.
So what are we doing with all this technology that we brought out? What I show here is kind of an interesting graphic that we're starting to use. If you're familiar with the storage pyramid, going from hot to warm to cold, this is kind of a different way of looking at it, and we think it brings out both the cost vector as well as the performance vector into one kind of pictograph. We call it the data sphere. And let me explain this. So you have the CPU, the central processing in the middle. This is where your information is being acted upon. And then out here is where your information is being stored for that processing. The closer you are to the CPU, the faster the performance, the quicker the information can be brought to and from. And then as you get further away, on this side, you're getting lower cost. So your cost per gigabyte or your cost for your storage is going down. And the amount of time it takes for that information to get to and from the processing is also longer. So on the outside edge, we show the hard disk drive. On the inside edge, we show the DRAM. And in the middle, you have non-volatile storage. And if you look at where we think 3D NAND is going to transform these economics is that the 3D NAND is much lower cost per gigabyte. And so you're going to see the use of transistor-based storage technology expand quite a bit in the overall data sphere of the market. And if you look at how that delivers itself in actual products, our first generation products, I'm going to talk about it in a little bit, we delivered basically 3 classes of products based on our first generation 3D NAND technology. You look at it from a performance per dollar standpoint, we took a standard hard disk drive, high performance hard disk drive, 10K hard disk drive, compared it to our new, the retail price of our new 3D NAND based SSD, and you see you're getting a huge performance improvement per dollar, IOPS per dollar. You're also getting a much lower amount of power use in that performance as well. So up to 217 times the performance per watt. And generation over generation, we significantly improved our endurance. So the endurance of the technology allows us to deliver at a very cost-effective density. We're able to deliver a much higher level of endurance as well, which ultimately, is going to come to more capacity within a certain given space.
Is the endurance a result of the physical, or is it management of cells?
It's both, but primarily you can think of it like we've gone back to 50 nanometer kind of nodes. So physically, the 3D NAND cells are significantly more robust. And on top of it, the whole error management scheme has been really maturing very fast as well. So together, that's the confluence of that.
Great question. Bring the questions coming too. So really, what this implements itself in is in our range of products that we introduced about a month ago. And we are reaching across multiple segments of the market with these products. Our first generation products are targeted at the high volume segments. And at a very high level, we're bringing PCI Express capability into SATA price points. So if you look at where cost per gigabyte for performant SSDs were on the SATA side, both in data center and in consumer, we now have a PCI Express NVMe-based product family that fits in that same price area. So really transforming the economics of it from a interface and a performance per gigabyte. And then we also brought out a SATA-based product line as well that allows us to get to lower price points. So like I talked about earlier, we're starting to see now some of our innovative customers are now offering storage services that are priced below SAS hard drive-based storage services, and they're doing it based on our new 3D NAND-based SSDs because of the cost per gigabyte and the performance capability that we're delivering with them. So we have a range of products in our cloud and data center, just so you know the names. We have our DCP3520. P stands for PCI Express. 3520 is the product name. And then we have a new S3520, which is our SATA-based product as well. These are targeted mainly at read-intensive type usages, although the endurance does go up. It's not a high endurance type drive, so it's designed for mostly read, also designed for dense type solutions as well. So because of the cost per gigabyte, the PCI Express product coming in at SATA type price points, you now can start to see some very dense PCI Express based storage offerings being available now. Embedded side, so Intel is branching out into the embedded market with their SSDs. We offer a long lifetime promise with these products, and we're bringing our 3D NAND to our embedded product family as well. We have both M.2 and 2.5-inch versions for the embedded product line. And then on the client side, we have both professional drives that work with our vPro features and add additional security capabilities. And then we also have our consumer, kind of high volume consumer line as well. Also focused on M.2. So just a little bit of detail about a couple of the data center products here. So the first one is the P3520. Number one, we're giving you reduced latency and performance at the same SATA-like price point. So for customers that are looking at a certain cost point, they can now get significantly faster performance, up over 4x performance on some of the workloads, and significantly reduced latency. And because of that, like I said, you're getting the IOPS per dollar, and the density for NVMe type solutions are going to start to expand. So you already see, if you follow like the chassis vendors and kind of the ecosystem that's needed, you're now starting to see a wide range of chassis solutions that have 24 or 48 NVMe drives on a single backplane. And so you're going to start to see now NVMe is going to move from being a caching tiering layer into your high volume storage layer as well. And this is the type of product that's going to enable that to do it in a cost-effective way. And then, of course, at Intel, we spend a lot of time on our validation and our silent data corruption protection, as we've talked about in a previous Tech Field Day. So we're bringing all that integrity and consistency of performance into this product line as well with our new 3D NAND PCI Express drives. On the SATA side, The key thing is, number one, it's higher endurance versus the standard endurance SATA drive that we had before, and a much lower cost. So really, the key advantage of the 3D NAND is higher density, and so we're bringing that density as a cost benefit to our customers with our S3520. So to wrap it up, so this is just the beginning. We're going to be producing products on our 3D NAND technology into the future as far as we can see. We've got a very exciting roadmap that we're working on. We can't wait to get to our next generation of this technology. We've got some new variants of NAND as well that we're going to build on this technology. And when you pair it with what we're doing at the high performance layer with our Optane-based products, we think we're going to have some pretty exciting combinations in 2017. So we see our products expanding from the 7 we announced today to over 17 in 2017, and we're going to expand the segments that we're covering as well. And you're going to see us also significantly increase the capacity of the drives themselves and the offerings that we have. So this is just the beginning of a very exciting time for Intel SSD products. So to sum it all up, basically we've spent many years working on 3D NAND technology. We have the best and the brightest people in the world helping us bring these products to market, like Pranav, and we're trying to transform storage economics. Through all the software initiatives that we talked about here, as well as the combination with this hardware roadmap and cadence that we're on, is really going to be an exciting time in the storage industry over the next 2 to 3 years as we see these transitions occur. And Intel is going to continue to supply you with not only innovative products, but also products that are validated and trusted to ensure that we can deliver products that meet the trusted capabilities that our data centers customers require. So with that, is there any questions? Any other questions you guys have on what we're doing on the SSD side?
So in the early part, in your part of the presentation, you talked about your particular, the way you do it, right? And I'm going to assume that's because you patented that, and that's why nobody else is doing it. That's first half of my question, or?
You mean like the floating gate thing, or?
Yeah, the floating gate bit.
You have to take a technology and work on it for probably 5 years. So the decisions were made long ago before anybody knew what everybody else was working on.
Okay.
So we've been working on this since 2011. And at that time, we did our paper analysis, we did experiments, and we figured this is the technology we want to land for XYZ attributes. And yes, we have all the patents, we have all the IP, but there's a large development cycle, development time that is needed. And that's another reason that, hey, once we announce something, for other people to do it, it's going to take a long time also. So it's not only patents, but it's also the effort and time and investment that it takes to actually do a different technology. Okay,
and then comparing that technology versus, because what I saw here was the comparisons of the 3D versus non-3D or 2D, right? What about the advantages of that technology from a customer standpoint, comparing it against competitors? Like, doing this way, that, like, I saw one that was like an 11% difference.
Yeah, so that's the stark difference. So to play more on the 11%, what it does is one technology, the floating gate, is smaller than the other.
Right.
So by definition, you're getting 11% smaller something, right, and which means, in a rough way, 11% more of capacity. That capacity can be used any different way, meaning it can be, hey, your cost is better or some attributes are better, you can have more over-provisioning, it can be more endurance, it can be more random performance. It can be unleashed in any way, but you are set up in a better technical spot to optimize your drive from there. So that's an example that, hey, your cell is just directly smaller. In addition to that, you can all technologies effectively are engineering optimizations, meaning you take a problem, you hack at it, but intrinsically some are superior and some have some issues inbuilt into them. So some technologies, not ours, have something like charge loss, very quick charge loss. So you have to manage around that, otherwise data integrity becomes an issue, or maybe just performance or quality of service becomes an issue, kind of a thing. So you have to manage that. Can be managed, but it creates, you're starting at an inferior point and then you have to put a whole bunch of wrappers around it. Floating it does not have those kind of issues because, hey, it's a proven technology. So The user will experience that in terms of many different things: quality of service, random reads, performance, all those things. So that's the level of advantage.
Okay.
Great question. Any other questions?
I'm curious about who's buying these and what you expect to buy. You know, if there's a way to differentiate between hyperscalers, traditional data centers, and consumer.
So obviously we have a wide range of products. So in the data center side, our P3520, where I'm seeing the most immediate interest, are the people who want dense storage, but also the highest performance. So they're investing in the building blocks they need for dense NVMe-based storage solutions. So as I mentioned, there are some emerging chassis coming out, things like that. So that's really where the P3520 is generating the most interest.
Yeah, I was looking for color on the types of businesses that are buying them. You know, for instance, cloud service providers versus, you know, large data center operators like Citibank or, you know, the Facebooks, Microsofts, Amazons versus, you know, is there a way to cut that out? You know, or?
Yeah. So the S3520 universally applies. So lower cost SATA SSD, high performance, you know, standard endurance. That's going to apply everywhere. So you're going to see any storage customer looking at that product.
Yeah, but you must have numbers that show who's buying it.
Pardon me?
But yeah, I mean, it's attractive to all of them.
Yeah.
But who is buying them? And I mean, can you split out what those, you know, roughly what are the percentages? Are hyperscalers buying 80% of them, 60% of them, or?
I would say
where are they shipping to?
Well, the S3520 right now, it just came out about a month ago, so it's mainly shipping to people who are qualifying the product. So we've got a lot of people who are qualifying it. So again, you're going to see it everywhere. You're going to see it in enterprise solutions. You're going to see it in very dense storage solutions. You're going to see it in also, you know, very unique solutions that some of our storage innovators are building as well. So that one's really a universal product. The P3520 is kind of a beachhead into new systems. So, you know, your larger OEMs, their cadence is not, you know, they don't introduce new chassis and complete systems every 6 months, right? So that product, the initial users will be the more innovative providers, the ones that are maybe a little more nimble or agile. And then as you see our larger customers transition, enterprise customers, transition over into the next generation Intel platforms, our next generation Intel Xeon, that's when you'll start to see a lot more dense NVMe offerings being available. So the initial buyers of the P3520 will be your more nimble cloud providers, you know, smaller channel, innovative type customers, and that's where you're going to see it being used first.